Okay, here's the second part of the section 7.5. This should be a much shorter bit. Um, so we're looking at the remainder estimate for the integral test. Now this is probably one of those subjects for me where I look at it and I say, gosh, this seems like a confusing theorem. It's not really that confusing. What I'll start with here is explaining the theorem, explaining a little bit of the reasoning of the theorem, and then we'll apply it to a particular problem. So we start off with this setup here where we say the remainder, which is defined as the difference between the actual sum and the first k terms of the series, is somewhere between the integral from k plus 1 on and the integral from k on. So it's really kind of a converse of the theorem we looked at with the integral test. If we look at it again, a decreasing series, it doesn't really matter which one it is here. Here's 1, 2. The idea is that sometimes this and this is much easier to compute than the actual series, right? We know that already. We've seen situations where that's the case. So the integral is the area underneath the smooth curve. One of these, okay, is basically starting from k, that's this one, and one of these is starting at k plus 1, pardon me. So we're not necessarily starting at the first term, but the idea is suppose we've summed up and we've got the right sum for the first so many terms. We've got the first here, plus that, plus that, plus that, and so on. Now we've got up to the first few terms here, and now we want to figure out what's left. Well, what's left is somewhere in between the right Riemann sum and the left Riemann sum, and that's what this is saying here. What's left is somewhere in between those two numbers. So we sum up the first few, then if we want to figure out what's happening after that, it's somewhere between if I start here and I take a left Riemann sum, or if I start here and I take a left Riemann sum, right? Again, starting here and taking a left Riemann sum is the same as starting here and taking a right Riemann sum if we start with k plus 1. So a left Riemann sum is starting at k, and a right Riemann sum is starting at k plus 1. So the actual value is somewhere between these two values because the integral is between the two. Okay, and that's what this is saying here. Okay, that if we go out k terms, want to figure out what's left, well, it's somewhere between if I take the integral from that stopping point to infinity and if I take the integral from one more than that stopping point to infinity. Okay, that's the idea here. All right, so let's look at how this works in practice. Now, this idea of computing the error term in a series is a very important idea that we're going to be using shortly with things like Taylor series. So we need to have this idea down. So here's a situation here, and the question is, what kind of error do we have on this particular, or what's the remainder? What kind of error do we have in this particular situation? So let's see here. So we know we've gone out 5 terms. Okay, and so we know that the remainder at 5, okay, after the 5th term, okay, is going to be bounded below by k plus 1 to infinity of, what is this, 1 over x squared dx, and bounded above by k, in this case it's 5, right, 5 to infinity, so this should be 6 to infinity, 5 to infinity of 1 over x squared dx. So whatever's left over has got to be less than this number. So in a sense, we can think of that as the error. The remainder, whatever's left over, the difference between this and the real value is going to be less than that. Let's compute it. Okay, we know we can do this. This is going to be the limit as b goes to infinity of, this is going to be 1 over x from 5 to infinity. So this is going to be the limit as b goes to infinity of 1 over b minus 1, oh, this should be a negative here, so plus 1 over 5. this goes to 0, this goes to 0.2, it's 0.2. So we know that the actual value is no more than 2/10 above this value. Okay? The remainder, the difference between this and the actual sum, is less than 2/10, less than 0.2. Okay? That's the idea. So we can get a sense of how far off are we. We know that no matter what this sum is equal to, we could actually compute the sum, but no matter what this sum is equal to, it's no more than 1.663611. Okay? It's no more than that. Okay? So we have now an upper bound on what could be possibly left over. Okay. All right. So the other thing we can do here is we can ask another question. How far out do I need to go in order to have 1 decimal place accuracy? Okay. So let's ask that question. How far out using this particular function do I need to go in order to get 1 decimal place accuracy? We're going to go back to this here. I didn't mean to do that. Okay. So how far do I need to go here to get 1 decimal place accuracy? What that really means is we want to make sure that the difference between the last term that we're summing and the finite sum, we want to make sure that it's no more than that. Okay. We want to make sure that that when we add or subtract, we can't add or subtract more than 0.01. Okay, and not just more than point. We want it strictly less than 0.01. We can't add or subtract more than that, because if we add or subtract more than that, we could change that digit. Okay, so what we need to do is we need to find a way to bound the value between that. So what we need is we need the remainder to be strictly less than 0.01. Okay, so we're going to do the same idea here. We want the remainder to be strictly less than 0.01. So since by the remainder theorem, let's go back and look at it. Since by the remainder theorem is always less than or equal to this integral, we're going to take this integral and make this integral strictly less than 0.01. Let's do it. Okay, so we're going to say the remainder will be less than or equal to, we'll make the remainder up to the kth term. Okay, we don't know how far we have to go, but we're going to go k terms to infinity, 1 over x squared dx, and we want to make sure that this is no bigger than 0.01. As a matter of fact, we want to make sure it's strictly less than 0.01. Let's solve this. Okay, I'm going to save this over here. That's over here. Let's pretend it's there. And we're going to go the limit from b to infinity of k to the b 1 over x squared dx. Okay. And that's going to be equal to the limit as b goes to infinity of, and this is going to be 1 over negative 1 over x from k to b, the limit as b goes to infinity of, we put in a b, get negative 1 over b plus 1 over k. Well, this goes to 0 because b is going to 0. This is just going to 1 over k, so this is 1 over k. And we want this, remember, to be strictly less than 0.01. Okay. So how, if k is equal to 100, okay, if k is equal to 100, then 1 over k is equal to 0.01. So I need k to be at least how big? I need k to be at least 101. If k is equal to 101 or bigger, that forces the remainder to be strictly less than 0.01, which means that there's going to be no way to change, after that point, there's going to be no way to change the first digit. Okay, so if I sum up to 101 terms, I'm guaranteed, even though I don't know what the actual sum might be, we might know what it is, but even if I don't know what it is, if I go to 101 terms, I'm guaranteed to get 1 decimal place accuracy. You can imagine situations where you don't know the actual finite sum here, right, or the infinite sum rather, but being able to estimate it up with a certain guaranteed accuracy might be useful. Okay, so that's all we've got. Just those two theorems. So I want to review a little bit of what we've done so far, just briefly, and that's the convergence tests we know, in order of suggested use. This is very cool. I love this little graphic. The first thing you always check is the divergence test. Remember, that is the test that says that does the sequence of terms go to 0. If they don't go to 0, it can't converge. The p-series test, that's where I have 1 over n to a fixed power. Okay, that's the p-series test. Okay, and that's where if p is strictly bigger than 1, it converges. If it's not, if it's 1 or less, it diverges. The geometric test is where not the base is changing, but the index is changing. That's where I have r to the n. Okay, the exponent is changing. Okay, not the base. Okay, the geometric test says that if r is between -1 and 1, it converges, otherwise it diverges. The integral test is what we just did. The telescoping series and partial sums, remember these kind of go together, where you try to figure out are terms canceling each other out as they go. Okay, so these are just the ways you want to go, and notice they basically go in order of difficulty. Easy. Find out if you can actually do it, right? P-series, can you set it up like this? Is p bigger than 1? Geometric series, can you set it up? Is r between -1 and 1? Integral test, telescoping sums, and partial sums all take a bit of work. Okay, that's why you want to do them last. Okay, thanks guys. We'll go over this more in class.